How does Dirac notation unify wave and matrix mechanics? Imagine trying to understand the tiniest particles in the universe. Two different ways have been used to describe their behavior: wave mechanics and matrix mechanics. But how do these two methods come together? That's where Dirac notation plays a key role. Wave mechanics, introduced by Schrödinger, describes particles as wave functions. These are complex functions that tell us the probability of finding a particle at a certain position or with a certain momentum. They change smoothly and follow differential equations. On the other hand, matrix mechanics, developed by Werner Heisenberg, uses matrices to representing physical quantities. These matrices act on vectors and focus on algebraic operations. Now here's the interesting part. Dirac notation, also called bra-ket notation, creates a common language for both. It treats quantum states as vectors in an abstract space called a Hilbert space. These vectors are written as psi, called kets. Observables like position or momentum are represented as linear operators that act on these vectors. If you want to connect the wave function to this abstract view, you look at the projection of the state psi onto a specific basis vector, like x for position. This projection is written as x psi, which is the wave function psi, x. It shows how the abstract vector relates to the familiar wave function. Similarly, matrix mechanics is expressed through matrix elements like phi of psi, where phi and psi are basis vectors, and a is an operator. These elements tell us how states transition or how measurements are made. What makes Dirac notation so powerful is that it doesn't depend on a specific representation. Whether you're working with wave functions or matrices, you're describing the same physical reality. The wave function is just a particular way to look at the vector, and the matrices are just a specific basis for the operators. This unified approach simplifies calculations and helps us switch between different views easily. For example, in quantum computing, sometimes it's easier to think in terms of matrices, and other times, wave functions are more useful. Dirac notation makes that switch seamless. In essence, Dirac notation acts as a universal language for quantum mechanics. It bridges the gap between the continuous wave picture and the discrete matrix picture. This connection is fundamental to understanding and manipulating quantum systems across many fields.